Hello everyone. So the topic of my presentation is quantum harmonic oscillator. Before going into the details of this interesting quantum phenomena, we will have to talk about the classical harmonic oscillator. Now, a harmonic oscillator is actually a system where force acting on a particle is directly proportional to its displacement from the center or the mean position and is always directed towards it. There are several examples of this regular classical harmonic oscillator that we also call the simple harmonic oscillator that includes a mass spring system, a simple pendulum, a ball and a bowl. And it is worth noting that all of those oscillations, they are linear oscillations because the differential equation that we form in order to describe its motion is d2x over dt square is equal to minus omega square x. Now you see that the power of your dependent variable, it's 1, which implies that it's a linear oscillation. And because of its linear nature, we see that it has several interesting properties that are exhibited. Like there is superposition in those waves, and the uh, distance that it covers on the one end of the extreme position is always equal to the distance that it will cover on the other end of the extreme position, and so on and so forth. But why is it important, and why is it ubiquitous? Because to be honest, it's seen everywhere, from a simple pendulum to a mass spring system to lattice vibrations to plasma oscillations, like from the smallest phenomena happening over here on Earth to grand scale objects like neutron stars and white dwarfs, and even in less dense space plasmas, we see those linear oscillations. And every linear oscillation, every wave is actually a simple harmonic oscillation in an appropriate co-moving frame. So why does that happen? Now imagine that we have any potential, v of x. We can always expand it using the Taylor series. And if we are talking about, let's say, smaller and smaller terms, we can actually ignore each and every term past the quadratic power term, which implies that your 1 by 6 d3b over dx cubed term would be neglected. Alright? But why so? Because we are taking x to be small, and for a small x, its cube, it's even smaller, negligible. And so is every other value that comes after that. Here, the second additive term will also vanish at the minima as the particle reaches equilibrium there. And if we take small oscillation into account, we can ignore all the terms past the quadratic power, giving us v of x is equal to v x naught plus 1 by 2 d2v over dx square at x naught multiplied by x minus x naught whole square. Hence the forcing term will become, since force is actually a negative gradient of a potential, it becomes f is equal to minus kx. Now you see the power of x on this forcing term. Again, linear. And this linear force is actually is a characteristic of your simple harmonic oscillation. And it is also worth noting that every force that we experience in nature, every force is linear in nature, at least locally speaking. And because of that, simple harmonic oscillations are ubiquitous in nature. But why do we need to go quantum? Okay, it's fine, it's nice, it works everywhere. Well, actually, it works everywhere, it works all the time until it doesn't. So, going quantum actually rectifies the problems that we face while working in a classical domain, because quantum realm is much different from the classical realm. It's highly non-intuitive, and it uses a different model. Now at times we start to see physics as an eternal truth and something that is like truth of the truth, and it can never be wrong, or it can never be different. Like if physics says that this thing would be like this today, that will stay like that forever and ever, but it's not true. Physics is a model, and to be honest, we have quite a lot of models in physics. So the model that we are actually acquainted to, that we see this universe through, is the Newtonian model. Quantum mechanics is a different model. So in that different model, we see that what we describe as characteristic of motion actually changes. Particles are not particles anymore, they are wave functions. You do not have forcing terms over here, especially in non-linear. Especially in non-relativistic quantum mechanics. And because of that, we actually have to stay content with its analogs. And we know that now, since we have to, go quantum, keeping that very system with us. So what we do is that we use its analogs. We see that in Schrodinger's equation that we are actually using over here as a replacement of your Newtonian second law of motion, we see that there is no forcing term over here. There is no forcing term in our equation of motion, but we do have a potential. And we can actually integrate our force over a given limit, over a given boundary conditions, and then we get this parabolic potential. And this is actually an analog of linear force in the quantum realm. So the Schrodinger wave equation for this parabolic potential would be minus h cut over 2m partial square psi over partial x square plus v of x psi of x is equal to e psi of x. After a little algebraic manipulation, means we take e psi of x to the left hand side and then take psi common, we get this beautiful expression where we have a second derivative added up to some constants, and then the first derivative, the only difference being that it's not really constant because of the presence of that potential. So what we will do is that we will turn it into the shape of a regular simple harmonic oscillator. We make some substitutions. We define 2m over h cut to be gamma, and this will give us our equation number 1, that d2 psi over dx square plus gamma e psi x minus 1 by 2 kx square psi into gamma of x, psi of x into gamma is equal to 0. Now we change our variables and we define capital X to be x over alpha. Oh, sorry, x over a, not alpha, sorry. Yeah, capital X to be x over a and gamma e to be epsilon. Here a and epsilon are yet to be found, okay? And we are using chain rule of differentiation, and because of that we may also say that partial scale x, partial scale psi of capital X over x square is equal to minus 1 over a square into partial scale psi of capital X over capital X square over partial capital X square. So yeah, that will actually turn our equation number 1 into partial scale psi over partial capital X square plus gamma alpha square e psi plus 1 by 2 k capital X square gamma alpha power 4 psi of x is equal to 0. Here 1 by 2 kx square gamma a power 4 is equal to 1, and uh, gamma ea square is actually equal to epsilon, alright? And this will actually give us d2 psi over dx square plus epsilon minus x square into psi of x. It's a really convenient uh, shape now, and if we take the limiting case where x is much greater than epsilon, we get this differential equation where d2 psi over dx square minus x square psi is equal to 0, and its solution would be psi of x equals ae to the power minus x square by 2 plus be to the power x square by 2. Now here we have two additive terms. The first additive term is great, looks nice. The second one, it does not follow the normalization conditions. If you multiply this psi with another psi, our integral, it'll explode. So yeah, a probability, it cannot be greater than 1 in psi star into psi. It cannot be greater than 1. But this thing, it will explode at several values of x. So yeah, we don't need this term. We'll just get rid of it. But in because of that, we need to write a as our g of x now. because you know it's a second order differential equation. It always needs to have two roots. So yeah, plugging in its value in the Schrodinger wave equation to find the value of g of x, and after some algebraic manipulations, we get d2g over dx here minus d minus 2x into dg over dx plus epsilon minus 1. Now it actually turns out that this is the canonical homogeneous linear second order differential equation known as the Hermite equation, and its solutions are in the form of Hermite polynomials whose general form is this. Henceforth, the solution would be like if g of x is equal to hn of x, so we'll write psi of x is equal to hn of x into e to the minus x square by 2, which is actually the mathematical representation of the eigenstate of quantum particles in the harmonic potential. It is also very important to make sure if our wave function is normalized, and if we generalize it, we get this thing. Psi n of x is equal to 1 over 2 power n into n absolute value into pi power 1 by 4 into hn of x into 1 into hn of x minus x square over 2, and this will give us psi naught of x equals 1 over pi power 1 by 4 e to the power minus x square by 2. We plug that value back into the Schrodinger's equation yet again, and differentiating this expression we get epsilon naught to be equal to 1. Previously we defined uh, gamma e to be equal to epsilon and a to be equal to 2 over k gamma power 1 by 4. Then gamma to be equal to 2m over h. And because of that, now putting all those values back into it, we get E naught to be equal to h cut by 2 into root of k over m. But k over m was actually defined to be omega square, and in that case root of k over m equal to omega. Here we arrived at the famous expression for the lowest energy value of the quantum harmonic oscillator, that E naught is equal to 1 by 2 h cut omega. This is actually really non-intuitive and interesting because the lowest energy value in every oscillator is equal to 0, but not in the quantum harmonic oscillator. It has a non-zero value. Of course, it's non-intuitive. What else would you expect? But you see, in this Hermite polynomial, we see a lot of discrete values. How do we go up and down in those discrete values to actually investigate or see what is happening to that particle in different energy levels? You guessed it right, because I gave you guys a spoiler. I will use the ladder operators in quantum harmonic oscillator. We know that the Hamiltonian for this case, for this quantum harmonic oscillator, is p square over 2m plus 1 by 2 omega square x square. Now we will actually define the lowering operator to be a equals 1 over root 2 into root of m omega over h cut into x operator plus iota into 1 over root of m h omega h cut into momentum operator. And it's a raising operator, it's its adjoint. Now you guys would be thinking that what the hell is this thing? Why are we going so complicated? Why are we defining those ladder operators to be so complicated? Of course, this linear operator, it has a tricky choice of prefactors, but as you would see, it'll turn out to be a very how should I put it, nice choice. Yeah, you would see it would be a nice choice. Apparently it's complicated. It's not Hermitian, which implies that it is not an observable. Ladder operators, they are not observable. And the position and momentum operator in terms of ladder operators would be these things, these lads that you see over here. Now, the only non-trivial commutation relation between those ladder operators is actually between A and A dagger, means your lowering and raising operator. And you see, it actually gives us a very simple and elegant commutator. If we had used different prefactors over here, our commutator would have turned into a psychopath. Yeah, so number operators, they are actually derived from your ladder operators, and they actually and they actually tell you about the number of eigenstates that are present in your system. And yeah, the number operator, it's not Hermitian. Oh, sorry, it is Hermitian, because its adjoint is equal to itself. And yeah, it's actually really important to know that it's an observable. We can observe this quantity. And yeah, it's commutators with lowering and raising operators are given as below. So why do we use this name, ladder operator and number operator? So first of all, the eigenvalue equation for this operator gives us this thing: n of mu is equal to mu of mu, where mu is in the kit formation. Now this mu is actually the eigenstate of your system. Now if you construct a new eigenstate where n is multiplied by your raised by your lowering operator, you would actually get this thing, right? The thing that is written right in front of you. And yeah, we would use the commutator that we have found previously, and we arrive at a conclusion that this actually gives you an a of mu to be equal to mu minus 1 into a of this thing, which implies that a of mu is an eigenstate with an eigenvalue of a of mu is equal to c minus into kit of mu minus 1. You see, it actually lowers the eigenvalue of your system by 1. Similarly, your raising operator, it does the same. So yeah, it actually, climbs one ladder, or climbs down, climb up or climb down one ladder at a time, and of your energy eigenvalues, and because of that we call it the ladder operator. And similarly, the number operator, it tells you about the total energy values. And well, you can also say that the ladder operator decreases the total number of energy eigenstates by 1, or increases it by 1. Why do we use it? Why care? Why bother? Now you see, we have this shape for our number operator, which actually reduces to the last term that we see in this second last term that we see in this slide. And if we define n plus 1 by 2 to be a term, we find out that this is strikingly similar to our uh, Hamiltonian of the system, right? Which implies that the Hamiltonian of a system in terms of number and ladder operators is this small and elegant thing. So yeah, it's really handy. It comes out really handy in different kinds of calculations where momentum and position operators are really difficult to come by. Results and applications. Now you see, those are the eigenstates of your system, and sorry, those are actually the states of your system, and there are only discrete values allowed. And as you can see, there is non-zero probability of you finding a particle outside the potential well, which implies that you can find that particle. If you have if you have a particle in a potential well over here in Lahore, there is a non-zero probability that you may also find that particle in London. So yeah, that is highly non-intuitive, really nice. Now this thing has applications each and everywhere, ranging from quantum plasmas to every low energy system. Like no matter what kind of curve you have, a parabolic, and a cubic nonlinear curve, a quantic nonlinear curve, even if it has a fractional transcendental nonlinearity, its bottom of that curve, it would always be, it would pardon me, it will always be linear in nature. And if it is linear, those calculations, they hold for it, and you would observe results very similar to the one that we have calculated over here. It is really important, it is really handy, and throughout the course of your careers, you will, yeah, see this thing and will probably use them. Thank you for your time.